Hi everyone, welcome back to Infino. We have finally come to the last question of the pack, example 4, which is the question being extracted from the 2020 HSC question 16b. For those of you who may probably know that this question is the last question in that 2020 paper, and that's why a lot of students said this question is a big boss question, which honestly it is, because you can try to imagine for those students who have to sit in the examination and under the time pressure in order to finish this question as the last one is not an easy task. And that's why for those of you who are watching this video, I highly recommend you stop this video for a while and at least give an attempt to it in order to feel the difficulty and before you watch the solutions. So let's give it a try. So now the question said, let In be the integration from 0 to pi over 2 and then sine 2n plus 1 2 theta d theta equals, and then the n is equals from 0 and then 1 up to infinity. And for part 1, it said, if I zoom in a bit, it said, please prove that the In is 2n over 2n plus 1, In minus 1, when the n is greater than or equals to 1. So that means like this one is, I think it's pretty straightforward common question type of the recurrence that correlate In and In minus 1. So this one, nothing special. Then if you have already watched the previous 3 examples, then the first part should be easy breezy. So this one should be by part. So let's give it a try. As you can see, like this is a long question, very long, 3, 3, 3, 2, in total like 11 marks. And that's why I've intentionally like split the parts into different pages in order to have a clearer explanation. So let's do B1 first, B1. So B1 said something like, if the In is integration from 0 to pi over 2 and then sine 2n plus 1 and then 2 theta d theta. So what should we do? Before we apply the integration by part, then we have to split the power 2n plus 1 into something like integration from 0 to pi over 2 and then sine 2n 2 theta times sine 2 theta and then d theta. And then we have to put u as the first part, u as sine 2n 2 theta, and then dv as the second part, which is the sine 2 theta d theta. So this question, the video may take a little bit longer, and that's why for those of you who are watching this video, be patient, because this is a big boss question, so pretty long. And then for the du will be, this part we have to pay attention. First of all, we need to apply power rule. So that means this one is 2n, and then sine 2n minus 1, and then 2 theta. But pay attention that you have to apply the chain rule here, and that's why you have to further differentiate the sine 2 theta, which is cosine 2 theta, and then once again chain rule, which is you have to derive the 2 theta. That's why you have the 2, and then d theta. And then this is the v. V is the integration of the sine 2 theta d theta. And you still remember, when you integrate sine is negative cosine, right? Negative cosine. So that means it's negative 1 over 2 cosine 2 theta. And then if I simplify it a bit for the du will be 2n times 2. Let me highlight it. 2n times 2 will be 4n. And then sine, and then 2n minus 1, 2 theta, cosine 2 theta, and then d theta. So you can see, like, for the du is already a little bit complicated than usual, but it's okay. We can still, like, just follow the flow. And let me open one new paper. And that's why we have to apply integration by parts. So as usual, in is uv minus integrate v du. Then this time will be slightly longer than usual. The u is sine, and then 2n 2 theta, and then times the v, which is negative 1 over 2 cosine 2 theta. Then, of course, like substituting from 0 to pi over 2 minus integration of the v, which is negative 1 over 2 cosine 2 theta du. Du will be, maybe I move it forward so that I can have more space to write the du, which is just copy it, 4n sine 2n minus 1, 2 theta, cosine 2 theta, and then d theta, and an integration from 0 to pi over 2. Okay. Then let's do some thought process. So this one is in. If I do some simplification, the first part, if the simplification is what? Is I can take the negative 1 over 2 at the front, and then I can have sine 2n 2 theta cosine 2 theta, and then substituting from 0 to pi over 2. Then as usual, this is negative, negative, and that's why it's positive. Any constant that I can take out? Any constant that I can take out? Yes, here. 1 over 2 and 4n, and that's why I can only take out 2n here. And then integration from 0 to pi over 2, and then sine 2n minus 1, 2 theta. And then I have cosine 2 theta times cosine 2 theta. And that's why I will have cosine square 2 theta. So far, so good. And that's why, if you can imagine the first part, when you do the substitution, what you will get, try to have a thought process here. If you substitute pi over 2, let's say this guy. Okay, just a thought process. If you substitute pi over 2, then you will have sine 2, and this one will be 2 times pi over 2. So that means, like, you will have something like sine pi. So if you're familiar with your trigo, sine pi is what? Sine pi is 0. But how about this part? This part will be cosine 2 times pi over 2, which is cosine pi. Cosine pi will be negative 1. Okay, and that's why you can see this part is gone. For the first part is 0. Then how about for the 0? Then just the same thought process. If you substitute 0, then this part will be sine 2n and then 0 times cosine 0. Cosine 0 is 1, but sine 0 is 0. That means that you can very safely and pretty sure that the first part after substitution will be gone. Okay, and that's why this whole monster will be gone immediately. This is 0, and that's why. Pretty nice, right? And that's why what we have to deal with is just the latter part. So let me try to copy it first. So which is in equals, like, again, want to be a little bit lazy, so I duplicated the latter part. Here. Yes, so 2n integration from 0 to power over 2, and then sine 2n minus 1, 2 theta, cosine square 2 theta d theta. Okay, and for that year, some students already get stuck at this stage, at this step, because like they can't really observe what to do next. But let me see. If I want to utilize the IN, what should we do? IN. So you can see the IN is this one. The right-hand side only got sine, right? That means that in order to utilize the IN, I don't want to see any alien. What do I mean by the alien is I don't want to see cosine. So that means like the thought process should be, I need to eradicate this guy. I don't want to see cosine anymore. Then what should we do? Then you should think of something square. Whenever you see cosine square, you should think of the identity, which is the sine square plus cosine square equals 1. Then, of course, like in this case, we have to substitute the theta as 2 theta. So that means like sine square 2 theta plus cosine square 2 theta is 1. Then let's do some transformation. So that means like the IN will be 2n integration from 0 to pi over 2, and then sine 2n minus 1, 2 theta. Then this one, I would change it to what? I would change it to 1 minus sine square 2 theta, and then d theta. Okay, so let me highlight it in green to let you guys like can see it clearer. And that's why I can do distribution again. When I do distribution, this one I will have IN equals like 2n, and then integration from 0 to pi over 2. So I distribute this guy to here, to 1. I distribute this guy to here. So what should I have? I should have sine 2n minus 1, 2 theta, and then minus. So mental math, 2n minus 1 plus 2 is the power, right? So that means like the power is sine 2n plus 1. 2 theta, square bracket, d theta. Then again, like we have to observe the given IN. Maybe I can copy it down for you. So maybe I put it in red box so you can see the IN. The IN, if I look at the question, the IN is integration from 0 to pi over 2 sine 2n plus 1. And then this one is 2 theta d theta. And that's why I want you guys to observe the IN is because you can see this guy is exactly your IN. But how about the first part? The first part here is what? Is your IN minus 1 if you look at the pattern, because the power is 2n minus 1. Some students may not be able to see it, but if you can substitute the n minus 1, so that means that maybe I can further explain here why this one is IN minus 1, because let's say here, if I substitute the sine, let's say I substitute the n as n minus 1, like this, then here will be sine 2n minus 2 plus 1. And therefore, this one is sine 2n minus 1, 2 theta. You can see. And that's why you see, like, the green guy, maybe I use another color. The orange guy, indeed is what? Indeed is when you substitute the n as n minus 1 in order to get the orange one. And that's why what is the orange one? The orange one is IN minus 1. IN minus 1. So that means that it is also very critical. Quite a lot of students, they can't observe that this guy is IN minus 1. They thought it is 2n minus 1 or something. But you have to really observe the pattern in the IN. So if you understand this, then probably you can finalize the final step, which is in equals 2n, and then this one is in minus 1, and then minus in. And that's why just simple simplification, 2n times in minus 1, and minus 2n times in. And then I can take out the in, which is in 1 and then plus 2n equals 2n times in minus 1. And therefore in will be 2n over, what is the format? What is the form given? Oh, 2n plus 1. 2n plus 1. In minus 1. That's it for the first part. If you ask me, the first part is not really difficult, but I think like the difficulty lies in, or maybe you can say like the tricky part is you have to observe the star part, that you need to observe, oh, the orange guy is indeed the in minus 1 term. That means that you substitute the original n as n minus 1. Maybe some students also get stuck in the trigo identity, but this one I would say if you have watched my previous examples or you have done some questions in trigo, there should be no problem. Okay, so this is the first part. Done, first part. Then how about the second part? So the next part 2 said we have to deduce that the in is 2 to the power of 2n and an n factorial to the power of 2 over 2n plus 1 bracket factorial. I think like for the first time that if we look at this part, maybe it's a little bit hard for us to know what should we do. But instead, we can look at what we have proved in part 1. In part 1, let me duplicate it. We have proved that the in is in this recurrence relation, which is 2n over 2n plus 1 and an in minus 1. So students should be able to look at the reduction formula relation, which is I reduce the power by 1. And this is a very good sign because like if you look at the n factorial is another concept that correlates the reduction formula relation, because n factorial indeed is n, and then n minus 1, n minus 2, and up to 3, 2, and 1. And that's why it is also in a relation which is in between n and n minus 1. So and that's why if I demonstrate, the I1 is what? The I1 will be 2 over 3 I0. And for example, like what is in minus 1? In minus 1 will be 2 bracket n minus 1 over 2 bracket n minus 1 plus 1 in minus 2. And if you further want to find what is in minus 2 will be 2 bracket n minus 2 over 2 bracket n minus 2 plus 1 in minus 3. And that's why we can start finding the pattern. The pattern is, let's say we start from in. The in is 2n over 2n plus 1 in minus 1. And then you can substitute the yellow part, which is this guy, into your in minus 1. And that's what would be in equals 2n, and then 2n plus 1, substitute 2 bracket n minus 1 over 2 bracket n minus 1 plus 1 in minus 2. And then you can further substitute the green part, which is this part, into your in minus 2, which is in, maybe save some time, let me duplicate it, and then duplicate, and then I delete the in minus 2, and replace it with 2 bracket n minus 2 over 2 bracket n minus 2 plus 1. The problem is like then where should we stop? According to the pattern, because like the n factorial should stop at 3 until 2 until 1, and that's why this one we should stop at ... should be stopped at I1 then, the first term. However, what is I1? I1 indeed is this guy, and that's why I can further replace the I1 as I0 in terms of I0, which is 2 over 3 I0. But what is I0? Anyone can tell me in front of the screen, like what is I0? So indeed, like the I0, you have to find it yourself. So this is also the critical part, that you have to substitute the 0 back to the original given IN. That means like here. So you can see when the n is 0, then this one will be integration from 0 to pi over 2 sine, and then this one will be 0 plus 1 is the power, which is 1, 2 theta, and then d theta. So this one will be negative 1/2 cosine 2 theta, substituting from 0 to pi over 2. So this one will be negative 1/2, and then cosine pi is negative 1, and a minus cosine 0 is also 1. So that means like this one is negative 1/2 times negative 2, which is positive 1. So some students said, like, if I substitute n as 0 into this part, does it work? The answer is no, because the domain given in B1 is that n is greater than or equals to 1. So that means at least 1. So it doesn't match with the domain in B1. And that's why if you can find the I0 is 1, then it's easy now. So that means like this guy is 1. And then we can observe the pattern, because you can see now the numerator is 2n. Let me highlight it in maybe red. 2n, and then suddenly 2n minus 1. That means like this guy, and then suddenly n minus 1, and then n minus 2. Okay, and then the denominator is what? The denominator is 2n plus 1, and then 2n minus 1 plus 1. It seems like no correlation, right? No correlation. And that's what we have to find the pattern by expanding the bracket. That means something like this. We have to do like IN equals like the first term, let's say 2n over 2n plus 1. And then I still have like 2 bracket n minus 1. And then this one, if you use some mental math for the yellow part, this is 2n minus 2 plus 1. So indeed, this one is 2n minus 1. 2n minus 1. And then further on, like this one is 2 bracket, and then n minus 1, sorry, n minus 2. And then this one will be mental math 2n minus 4 plus 1, so 2n minus 3. 2n minus 3. Then dot 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 2 over 3 times 1. So far so good. And that's what should we do next? The next thing is we really have to kind of like be able to observe the pattern. The pattern is there's missing something in between, because like you can see this one is 2n plus 1. Supposedly the next term should be 2n, right? 2n. But now it becomes like 2n minus 1. And then 2n minus 1 next term should be what? Should be 2n minus 2. but now it becomes like 2n minus 3. Okay, and that's why we have to do some adjustment. So in, you have 2n over 2n plus 1. Let me use black to indicate that's the original term. And then you have 2n minus 1. And then this is 2n minus 1. And then originally you have 2n minus 2. And then this is 2n minus 3, dot, 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 2 over 3 times 1. And I use red one to multiply the middle term, which is 2n and 2n minus 2. But I have to do adjustment for the numerator, which is 2n and 2n minus 2. And indeed, you see the denominator is already in a series, or you can say factorial relation. But how about the numerator? The numerator, let us check. This is 2n. This is also 2n. And then this is 2. And then n minus 1. If I take out this guy, what is it? This guy will be highlighted. This is critical. If I take it out for the 2, then it is n minus 1. So that means that you can see, if I take it out for the 2, this is n minus 1. And that's why can you see that it is already in recurrence relation, because this is 2n, this guy will be 2 bracket n minus 1. And that's why I can foresee this term here should be 2n minus 2. Is that clear for the pattern? And that's why, let me try to take out for the common factor. The numerator is, let's say, let me highlight it in yellow. If I take it out for n minus 1, n minus 2, and then up to the end, and that will be this part. n minus 1, n minus 2, up to the end. This one will be the yellow part. Oh, and then we have to take out the 2. Then the 2, you have to pay attention, because like I intentionally use black and red. If I highlight it in pink first, for the black 2, 1 and 2, and then 3, and then up to the end. How many 2s do I have for the black 2? How many terms? Should be n terms, right? And that's why it should be 2 multiply itself for n times, which is 2 to the power of n. Then let's say if I use orange to indicate the 2, the red 2, 1, pink, orange, 1, and then the 2 taken off should be this one, and then next one should be 2. Then how many terms? Starting from n up to the n will be 1 as well. So that means like n terms again, n terms. So maybe I use red, 2 to the power of n. And then this one will be n, and then this guy, n minus 1, n minus 2, and up to 1 as well. Denominator shouldn't be too hard. What is that? Should be factorial. Starting from what? Starting from 2n plus 1. 2n plus 1. And that's why the final answer will be, I have 2n square, and then I have n factorial square, and also like the denominator will be 2n plus 1 factorial, and that's why the final answer will be 2 to about 2n, and then n factorial square over 2n plus 1. And this a little bit crazy question is done. Okay, so far so good, right, for the part 2. This video will only cover the first 2 parts. If you have any questions, feel free to comment below, and don't forget to like and subscribe to our channel, and I will see you next time for part 3 and 4. Bye bye.